are exerted on a crate. So the net horizontal force is what?
40 to the left.
40 to the left. All right. Okay, good. Oh, this is gonna be.
Just because you're a teacher can't mean it's getting crazy.
Yeah.
No pressure.
Okay. Okay, choose the free body diagram that corresponds to the situation below. A cable pulls a crate to the right across a floor at constant speed. So now, hang on, if it's moving at constant speed, what does that imply?
Yeah, it's going to be in the middle.
Okay, raise your hands, please. Yes, sir. They're equal in magnitude. Good. So the net force would have to be 0, right? Okay. So that means the vectors have to be the same length. We know in a free body diagram they always start at the object and emanate from the object. Yes, sir.
Are you recording this?
I am recording this. Yes. This will be the second.
Go on.
If you haven't seen it, this will now be the second chapter 6 review, test review up there. So, okay, so now we got to get this right though. If the crate is pulling to the right, which vector should be going to the right? Tension. Good. Tension to the right, friction to the left. So that looks like a winner right there, doesn't it? Okay. Okay, good. Okay, how about this? The instruments attached to a weather balloon have a mass of 5.47 kilograms. The balloon is released and exerts an upward force of 103 newtons on the instruments. After the balloon has accelerated for 10.2 seconds, the instruments are released. A net force with a magnitude of blank acts on the instruments after they are dropped from the balloon. Okay, so talk to me about this. What's going on here? Haley, what's happening? Once those instruments are released from the balloon, how many forces are acting on them? Okay, so let's think about this again. So we got these instruments attached to the balloon. The balloon takes off, and it's pulling the instruments up in the air, right? Now, it's a little more complicated when it's actually lifting the instruments up. Then there would be, how many forces acting there? Two. What would they be?
Gravity and...
Okay, so you get force of gravity down, aka weight, and then the lifting force up, right? Okay, but once the instruments are released from the balloon, they're in free fall, right? Now, how many forces remain? One. What is it, Austin? Gravity. Yeah, mg, right? So all we got to do is multiply the mass times 9.8. Does that make sense? And that's going to give us the only force that's remaining there. Okay. So somebody with a calculator, quick, what's that give us? What's it give us? 53.6. Okay, we got how rounded appropriately, it sounds like? Okay, because we need 3 sig figs, so 53.6 watts. Newtons. Okay, there we go. All right, we're on a roll. Okay, you lift the basketball with your hand, accelerating it upward. What forces constitute action-reaction pairs? Let's review this real quick. So now, how do we define action-reaction pairs? What is it? What the forces have to be doing to be an action-reaction pair?
Actually, same object.
Okay, they have to be acting. No. How many objects are being acted on by an action-reaction pair? 2.
They have to be the same action, like the same force.
Okay, it has to be the same. Okay, it has to be the same magnitude, opposite directions, right? We had a recipe for this. We said that if we're going to call the action force A acts on B, then what's going to be the reaction force? B acts on A, right? It's just opposite in magnitude. Okay, but forces act between objects, right? So forces always occur in action-reaction pairs. You can't just have a force acting out of nowhere. What's the action-reaction pair that's acting on this pen if I release it? Okay, gravity is the force, but name the action force.
So the
There is not a.
Okay, here we go. So if we're defining the action force as Earth pulls on pen, then what's the reaction force? Pen pulls on Earth. Okay? So let's look at these then. If we're lifting this basketball with our hands, let's see if these would work. The gravitational force exerted on the basketball by the Earth's mass and the force exerted on the basketball by, that doesn't work, does it? It doesn't work for a bunch of reasons. It just doesn't fit the profile. It doesn't, we didn't flip around A acts on B, B acts on A, right? And also, notice that both of these forces are acting on one object. That's not the way action-reaction forces work, right? They act between two objects, okay? So that one's out of there. What about number 2? Gravitational force exerted on the basketball by the Earth's mass and the force exerted on your hand. Now, right? How about number 3? Force exerted on the basketball by your hand and the force exerted on your hand by the basketball.
Yeah.
That's good. There's a winner. Okay. Force exerted on the basketball by your hand and the gravitational. No good. And then gravitational force exerted on the basketball by the Earth's mass and the gravitational force exerted on the Earth by the basketball's mass. Aha, that works, right? Everybody see that? Those are the two? Okay? Good, good. All right. A person stands on a scale in a stationary elevator. The scale reads 479 newtons. What would the scale read when the elevator is moving downward at a constant speed of 2.30 meters per second? Same thing. How come?
Because it's constant.
Okay. Okay, good. Okay, let's attach some vocabulary to this. We got to kind of get the wheels turning here. We've been sort of in idle mode here for a few weeks, I'm assuming. So we know that when a person is standing in a stationary elevator, the acceleration is 0, right? And so the two forces acting are going to be in equilibrium, right? There's going to be the normal force, which the scale is measuring, pushing up on the person, supporting him. Then there's the person's weight pushing down, and they're equal and opposite in that case, right? Does that make sense? Okay. If the elevator were accelerating upward, for example, which of those two forces would they no longer be in equilibrium? Which force would have to be greater? If we're standing in the elevator and it starts to accelerate up, he is. Thanks. So which force would be greater? Normal force, good. The upward force, right? Because I'm accelerating upward. So there'd have to end up, in order for me to accelerate upward, that would mean there would have to be a net upward force, right? So the upward force would have to exceed the downward force. And so what would the scale would actually, and that makes sense. You could picture this, the scale would read more than your body weight then, right? Mm-hmm. If the elevator were cruising along at constant speed and moving upward and it decelerated, right, that would mean that there would be a net downward acceleration, right? Yes. So in that case, your weight would have to exceed the normal force and the scale reading would be less than your weight. Okay, but in this case, it's moving downward at constant speed, no acceleration, right? So they should still be in equilibrium, right? Make sense?
Yep.
Okay, so the answer is 479. Good. All right, so far so good. Okay, how about this? Choose the free body diagram. So a rocket is propelled vertically through the air by its engines. The rocket's velocity increases with time. So the two forces, it looks like, we're going to call thrust and gravitational force, right? Which one has to be a bigger vector? Thrust does, because it's increasing velocity upward, meaning positive acceleration upward, right? Okay, does that make sense? Right? So then the upward arrow should be the thrust arrow, and it should be bigger, like that one right there looks good, right? Everybody agree? Okay. Everybody agree that's going to give us a net positive force upward? Okay. Wow, that's choices. All right, back to the balloon. So mass 4.72 kilograms. the balloon is released and exerts an upward force of 80.4 newtons on the instruments. The balloon and instruments experience an acceleration of what? So we need to write some stuff down on this one. Right? We need to draw a free body diagram. Okay. Okay, so what's our free body diagram going to look like here? What are the forces acting? Okay, gravity and lift force, we'll call it. Okay, so the upward arrow is going to be lift force, right? So we'll just call it F sub L, how about? Downward is force of gravity. What's that always equal to? mg. Good, good. Okay, and so that's it, right? So what's our equation of motion? There's only one in this case. So, okay, so the net force is going to be lift force minus mg, right? That's my net force. Equals ma. Good, and we're trying to solve for a, aren't we? Right? So everything else we should know. It looks like we do. So if I divide each side through by m, we get the equation A equals lift force minus mg over m, and I can just plug stuff in there, right? So what's that give me? If I plug in values, I'm going to get 80.4 minus 4.72 times 9.80 divided by 4.72. Everybody agree?
Yep.
Okay, so if we plug that in, what do we get? So we got the quantity 80.4 minus 0.72 times 9.8 divided by 4.72 is that. Rounded to how many places? 3 it looks like. So we get 7.23. What are my units going to be? Of acceleration? Meters per second squared. Good. Oops. Oh. That's what I want. Meters per second squared. How's that look? Oh, look at that. Good deal. All right. How about this? You lift the bowling ball with your hand, accelerating it upward. What are the forces acting on the bowling ball? Is this asking for action-reaction pairs? No. This just wants all of the forces acting on the bowling ball. So the force exerted on the bowling ball by your hand and the gravitational force exerted on the earth. We don't care about that, right? That's not it. Gravitational force exerted on the bowling ball by the Earth's mass and the force exerted on the bowling ball by your hand. There's a winner, right? Anything else?
Nope. They're all on.
No, those are all action-reaction pairs, aren't they?
Yeah.
Yep, that's it. Okay.
So if it doesn't say action reaction pairs, don't put action reaction pairs?
No, they just wanted only the forces acting on the bowling ball. Okay, so just imagine on that one, what I would recommend maybe is think of it in terms of a free body diagram. If you drew a free body diagram, what would all the arrows be? Right? You're just identifying what the vectors would be. Okay. Okay, we got a pendulum problem. No big deal. These are just, we just have to use our pendulum equation. There it is. right?
9.80
So what do we got?
1.65 2 pi squared.
Okay, what are we trying to find? The length of the pendulum. We're trying to solve for L, aren't we?
Yeah.
Right? So we want to algebraically isolate L. So what are the things we do to get the L by itself? Okay, first we're just reversing order of operations, right? So quick review. That's how we isolate. No addition, subtraction, multiplication, division. We divide each side through by 2 pi. That stuff cancels, right? Then we have to undo the square root. How do we do that? Square both sides. So that's going to give us t over 2 pi quantity squared equals L over G. Last step, multiply by G. So there it is. I just have to plug all that stuff in, right? So let's plug in those values into the calculator. So what do we get here? We get 9.8 times the quantity, period, which is 1.65, divided by the quantity 2 pi. You see why I need the quantity sign there?
Yeah.
Okay, because I've got two things in the denominator. I could have made a fraction template out of this. Maybe that would be better. Close the quantity that's being squared and square it. Does that look good? Everybody okay with that? So, looks like we got 3 decimal places. So what is that? 0.676. Good. And what are the standard units going to be if we're measuring length? Good. Okay, good. Oh, we're batting 1,000 right now. We can't mess up here. We got to get 100 on this. So how about this one? A 125 kilogram crate is pushed horizontally with a force of 539 newtons. If the coefficient of friction is 0.27, the acceleration of the crate is blank. Okay, this is a good one. We want to. This is one of the harder ones where we've got both horizontal and vertical forces going on, right? So we got to have 2 equations of motion. So let's go through this. Okay, so free body diagram. What's a force acting on this? Braden, what's one force acting?
Normal force.
Normal force is acting. What direction? Up. Another force. Okay, what's another force? Gravity. What direction is that acting? Down. Okay, how do I write gravity? mg, best way. I can write it as f sub g, but it's always just mg, right? Might as well write it as mg. Okay, what else is going on? Friction. Okay, if let's assume we're pulling it to the right, so then friction is acting to the left. And if it's sliding, what kind of friction is it? Kinetic. Okay. And then what's the force acting to the right? Tension, I guess, or pushing it, pushing force. Doesn't really matter. We'll call it F sub P for a pushing force. How's that? So there's my free body diagram. Okay? So now we got to write the equations of motion. What's one equation of motion here?
K equals
Okay, yeah, but the equation, we're jumping ahead a little bit. The equations of motion, remember, come from the free body diagram because there's 2 things going on here. We've got horizontal forces acting and vertical forces acting. They're independent of each other. Right?
Net force equals.
Net force and gravity have to equal.
Okay, so you mean, by net force, you said net
I meant
force,
normal force.
normal force, okay? So then, we've got one equation of motion is gonna be for the vertical forces, and that one is just gonna be the net vertical force, which is gonna be normal force minus mg. And how come? Explain that part right there to me, why?
Because they're not going up. It's just.
Well, how come that one's positive and that one's negative?
Because gravity's.
Because gravity's pointing in the negative vertical direction, that arrow is, right, the vector, I should say. And normal force is pointing in the positive vertical direction, right? So this combined, this is just the y component of the net force, right? And what's that equal to?
Zero.
Okay, it equals ma, but a is zero. It's not accelerating vertically, is it, right? So that's equal to zero. So there's one important equation.
The other one be the net force equals push force minus coefficient of friction.
Okay, good. So now we're saying to the right is positive, right? That's our convention. So the positive one is going to be the push force minus kinetic frictional force equals what? Ma, right? Net force equals ma. And this time there is some acceleration horizontally, right?
Then we can substitute.
And keep in mind, this is just right here. All that is, that's just the horizontal component of the net force, right? So those are our two equations of motion. All right, that's good. We're trying to solve for A, right? The push force is given to us. What about the kinetic frictional
U
force?
sub k multiplied by normal force.
Okay, good. We've got to use our frictional force equation for that, right? Our model. And so remember that from right over here, right? Kinetic frictional force just equals mu sub k, which is just the kinetic coefficient of friction, right? Times normal force. Let's just take a second and let's just kind of remind ourselves why that makes so much sense. That's one that if you kind of think about the way friction has to be this way, right? We talked about the bumpies being pushed together, so we know what's the force that determines how hard the surfaces are being pressed together? That's the normal force, right? The normal force is measuring how hard the ground is pushing upwards on is this a crate, I think, right? So that's telling us how hard the little microscopic bumpies are being pushed together, right? And what's this coefficient mean?
U sub a.
It's mu sub k. What's it really kind of mean? Like if I have a, say it again? Well, it's kind of like a ratio. Yeah. If mu is, what, it's going to generally reside between what values? What lower limits? 0 and 1. And in rare cases, it can go above 1 if you're kind of cheating. Right? But if it's close to 0, what's that tell you about the surfaces? Slippery, right? If it's close to 1, not slippery, right? There's a lot of friction there, right? A lot of traction. Okay, so
What would be a mu sub k that's more than one?
a mu sub k that's more than 1 would be like rubber being slid across a rubber surface, because the rubber deforms, and so the bumpies, it's because it kind of molds to itself. It's sort of like cheating a little bit. There's almost a little bit of adhesion going on there.
Okay.
Right. And what Cade was going to say is it's really then, if it's kind of tells you the ratio of how much force do you have to apply to push it compared to lifting it, is what we talked about in class. If you have to apply more force to push something, to slide it, than it takes to lift it, then that means a coefficient of friction that's greater than 1. Okay? That's pretty rare. So here's our model. We can make this substitution then. We could say that instead of mu sub k, we could write this frictional force in terms of mu sub k, which is given, and the normal force. And look what we get from our first equation of motion. What does this tell us? If I solve for normal force here, what's it telling us that's equal to? It's equal to mg, right? Because there's only two forces acting vertically. So we could say, okay, if I solve for normal force, it equals mg, right? And so if I plug that into my friction equation, if I combine those things, look what we get. Equation number 2 becomes F sub p minus mu sub k times normal force equals ma, and we know normal force is just mg, right? So you see the value of that thing. We're able to solve for a, because once we make that substitution, now we've got only stuff in here that we know values for, right, except for a, which is the one thing we're trying to find. Okay, so we end up with F sub p minus mu times mg equals ma. We know that, we know that, we know that, we know that, we know that. The only thing we don't know is a, so we're good. What do we have to do to isolate a? Divide by m. Okay, and we end up then with a equals, what do we got here? What are the numbers here? 0.2, okay, somebody write these down real quick so I'll forget them. So the mass is 125, 0.27, 539. So if I plug that stuff in, let's just do it right into our calculator. How about it? Save a little time. Pushing force was what? 539?
530.
So 539 minus mu was 0.27 times the mass was 125 times g 9.8. So there's the top, right? I'm just going to go ahead and get that answer divided by the mass, which is 125. Everybody see what I'm doing?
Yep.
Gives us that.
Boom.
Okay.
Oh god,
That's
that's
Satan's
Satan's
number.
number.
So 3 sig figs, everybody agree? So 1.67?
Yep.
Okay. Okay, what should my units be for this?
Meters per second.
Okay, it's an acceleration, good. Meters per second
Make sure you click the yep,
squared. There we
so it'll
go.
make it be wrong.
Are you speaking from experience?
I am.
Okay.
I don't know if it's this or Math Excel.
Oh!
Don't we only get our 2 significant
What?
digits? Yeah, I think we should.
Oh, you did 3 sig figs.
Oh, very good.
Got him.
Oh.
There we go. Darn it.
No, that's because you have to try again. Yeah.
There we go.
Half credit. Half credit.
Hey, did you see that earlier and just didn't say anything? You probably did, didn't you? Yeah, darn it.
Don't give that much credit.
All right. How about this one? How much time we got?
We have 12 minutes.
Oh, we can do it. We can do it. Here we go. Back on track. Okay, put those phones away if you got phones out. Okay.
I'm sorry. I'm not being your shield any longer.
So let's talk about this one. A 64.7 kilogram boy and a 47.6 kilogram girl use an elastic rope while engaging in a tug of war on an icy frictionless surface.
That's not gonna be.
Okay, so the acceleration of the girl toward the boy is 2.7 meters per second squared.
That's
So they're
romantic.
saying that
Okay.
the boy's stronger than
No, not at all.
Yeah.
No.
I like how you use the same 3 numbers, just rearranged.
That was totally
Was it?
unplanned. Yeah.
Was it?
How about that? What?
Like 6
Oh,
4
yeah.
7.
What are the odds?
7 6.
Look, we could calculate them, but we won't. Okay,
I
so
think we should.
They were just saying
talk to me about this. What's going on with this? Abby, what's happening here?
heavier.
If I've got the boy and the girl are pulling with this elastic cord, right?
Oh, it's elastic.
Okay, and that doesn't even really matter, honestly. That doesn't really make any difference. The cord, now think about that. That's just a line, right? When we use a line like that, it's just an extension, really. I mean, they might as well. The same problem would be if they were just holding hands and pulling each other, right? Pulling each other.
So
right?
romantic.
More romantic.
Yeah.
But they've got this cord, which just allows them to be further apart. Yeah, I'm a chaperone.
That's good.
All right. So what's going on here? What do you think? What kind of situation does this sound like? Girl pulls on boy.
Flirting?
Boy pulls on girl.
Okay, what's that sound like?
Reaction.
Action, reaction, pair. Aha. Okay. Now, we'll be able to look at this very shortly from a slightly different perspective. We could take the same problem in a couple weeks, and we'll talk about it using conservation of momentum. And we'll get the same result. But for now, the way that we have to deal with this is we realize if we look at the recipe, force of boy pulling on girl, girl pulling on boy, those are an action-reaction pair. So they have to have the same magnitude. And so how is it helpful to us? Why is it helpful to know that the girl accelerates with a magnitude of 2.7 meters per second squared?
That's the acceleration.
Well, okay, not necessarily. What is it that's equal and opposite there? Accelerations? No, what is it? Forces. Right? The forces acting on the boy and the girl are the same. But are the accelerations, would you expect them to be the same?
No, they're different because they're different. Yeah, different.
Aha, they're different masses. And so the accelerations should be different, right? Who's probably going to have a bigger acceleration? The girl, because she has less mass, right? Okay, so all we'd have to do then, how might you set this up?
Yeah.
So how could you maybe set this up? How are we going to do this?
No,
The net force,
Acceleration equals the boy's mass times.
there you go, exactly. MA equals MA, right?
Appreciate it.
Okay, so we get mass of the boy times acceleration of the boy equals, now we're just doing magnitudes. They're going to be opposite signs, right? But we're just looking at magnitudes. Equals mg ag. What are we trying to find? Okay, we're trying to find that. So all we have to do is divide each side through by the mass of the boy, right? And we end up with a sub b equals m sub g, a sub g over m sub b. So what is that? 47.6 times 2.7 divided by 64.7, right? Okay. What's that give us? 2.0. To how many sig figs? 2 sig figs. Good. What are the units? And the units are going to be meters per second squared. The direction of the boy's acceleration is toward the girl.
If the surface is frictionless, would they even be able to stand? Like, I mean, obviously.
No, you're right.
I was just.
There we go. Last one.
This is the one that,
This is the one. This is the one.
It was so funny.
Just gonna get all the other way.
Because he's huge and then Jacob gave
I just need to get all the other ones right.
I hit my head on the wall. Well, I guess I thought there's only one player.
Okay. So let's talk about this. They give us the mass of the car. They give us the initial velocity of the car. You slide to a halt in a distance of 40.8 meters. Okay. The coefficient of kinetic friction between your tires and the icy road is what? So we're going to need a free body diagram here. What are the forces? We've already done one. In fact, we could just go borrow, essentially, almost borrow, the free body diagram from before with the crate. There's one key difference, though. So what are the forces acting, assuming the car is moving to the right, what are the forces acting on the car? Okay, good. So we had gravity just like before.
Oh, this is.
We had what's acting up? Normal force. Okay, what else? Friction acting in which direction?
Left.
Okay, any other forces? No, that's it, isn't it?
But what about the car still sliding?
Okay, you're right, it's still sliding, but that's really not, there's not a force that's causing it to slide, right? Because an object, what does Newton's first law say? An object in straight line motion,
Stay in motion.
stay in motion
Yeah.
unless acted upon by an external force. Okay, so, all right, so in this case, if there were no forces acting, the car would just continue to slide at constant speed forward, right? But there is some frictional force, which is opposing it, which is actually causing it to accelerate a little bit, right? Slow down. Okay? All right. So then, if we write our equations of motion here, they look pretty familiar. Ian, what's going to be the vertical equation of motion? Yeah.
Yeah. Or like going up.
Yeah. So what's the?
Is it F N minus a G?
Yeah. Normal force minus weight
Right.
equals.
M A. Right.
Okay. And what is the vertical acceleration? Zero.
You're welcome.
So normal force equals mg is what we decided from the last case, right? We solve for normal force. Okay, the other equation of motion is pretty simple. There's only one force acting. So horizontally, what's the only force acting? Good. Frictional, kinetic frictional force, which is negative, right?
Equals net.
Equals ma, right? So all we'd have to do then is, if we want to know what the coefficient of kinetic friction is, well, we got to make a substitution here, don't we? Right? We know that kinetic frictional force is just mu times normal force, right? So would everybody agree that this part right there is just going to become minus mu sub k times normal force, which is just mg? Everybody agree?
Yep.
If we skip a step there? Okay, and that's equal to ma.
So the mass doesn't even matter.
So, yeah, so really the mass doesn't even make it any difference here, does it? Okay. We could cancel it out. If I want to know what the coefficient of kinetic friction is, I'm just going to divide each side through by negative g, right? Everybody agree?
Yep.
And what's the problem? What don't we know?
Acceleration.
Ah,
So
okay.
you use kinetic stuff.
Okay, so to find acceleration, this really goes back to a kinematic situation, doesn't it? They give us a bunch of kinematic quantities, and we've got to solve for A. So let's go over and just separate out a little part here for kinematics. So what are the quantities that we know, the kinematic quantities? Initial velocity is what?
11.2.
11.2 standard units. What's final velocity? 0. What else? Okay, displacement.
We're gonna use.
Right? What are we looking for? A. Okay, so it's number 4, isn't it? It's the one with no time. Right? So then we end up using v squared minus v naught squared equals 2a delta d and just solve for A. Right? Everybody agree? And then we can fill in A. How, are we going to make it? We're going to make it, aren't we? 3 minutes, we can do it. We can do it.
Got 1 minute.
1 minute's all we have?
Yeah. Actually, you got like 25 seconds.
Got the
Okay.
point.
Well, you get the idea, right? We'll solve for A. And then I can solve for B, right? Okay.
Actually, true.
Dude, 10 minutes.